main reason we do these so that we can build a rapport with you guys to help you keep the plant running longer, whatever their application is. And we found that if we give you information, you understand what's going on in the pump rather than just being expected to work on it. And that's what we're going to go over first here is a little bit of hydraulics. What is going on in the pump? How does it operate? Why does it do the things that it does? And what happens when we inadvertently add things to the system or change. So we're going to go over some hydraulics first. Some of it will seem pretty remedial, but it's all basic stuff. You got to have the premise before you can go on to the next step. So pump and fluid basics. First off, there's two classifications of pumps. For the most part, we have centrifugal over here, positive displacement over here. Roughly in the world, of all rotating equipment, about 68% of all rotating equipment in the world is a pump. That includes generators, engines, a whole thing. So there's a lot of pumps out there. And within that, about somewhere around 86% are centrifugals. So a lot of centrifugal pumps, a lot of different variances, kinds, and so on and so forth. So there'll be centrifugal pumps. It is a pressure creating device. And when we say that, just keep in mind that it's only going to do is what pressure it can possibly provide. So from that standpoint, it converts velocity energy to pressure energy. Is everybody kind of getting that? The faster you turn it, the more pressure you're going to get. The flow is only dependent upon the system characteristics. So obviously when we talk about system, we're talking about the suction side, the discharge side, the tank, everything involved in that system, not just internally in the pump. Positive displacement pumps, if you want to look at it, they are just the opposite. They are a flow creating device. You have a specific cavity internally in the pump. First off, everybody go around the table, give me an example of a positive displacement. And you can't use the same one twice, so go ahead. Roper, for you. Roper.
Yeah.
Gasso, good one. You have some at your plant, the Tut Hills, because each.
I call them acid pumps.
Acid pumps, okay. Yeah, the Tut Hill, because it has a specific cavity internally. Every rotation is going to provide X amount of flow. So every rotation, every gear, every whatever it may be, is going to provide a certain amount of flow. You can actually calculate the volumetric capacity if you knew how much, the stroke, the length, the bore. On a gasso, on a piston pump or a plunger pump, it's easier to figure because you have a round bore and the stroke. You know exactly how much it's going to produce every time it throws that piston or plunger. Does that kind of make sense?
Yeah. That hill's not the only positive displacement pump we got.
Corkins.
Yeah.
The Corkins, they got some vane pumps. So again, whatever the distance is between those two vanes as it comes around is going to be your volumetric capacity. Well, every time that vane comes over, it's going to produce X amount of flow. With you, on the ropers, every time the roper fills the gears, every time it rotates, it's going to fill a certain amount from that standpoint. Does that make sense? So we know, like on the ropers, that you take a model 3648, we know that it's 0.48 gallons per revolution. Every time that thing rotates one time over, well, the shaft, 360 degrees, it's going to produce 0.48 gallons. Okay? Tony?
No, I'm not sure, but I think it's a Fristam.
Fristam's going to be a centrifugal.
Is it? Okay.
Yeah, it's still going to be centrifugal, but you got your worn rups, your diaphragm pumps.
Okay, all the diaphragm.
The old SA2As,
Yeah, I didn't think
Every stroke, it's basically that diaphragm has a volumetric, it's going to produce a certain amount of flow. Every time that thing strokes. The other ones you have a lot of is the old PC pumps, progressive cavity, screw pumps, the Moinos and so on and so forth. Every time that progressive cavity goes over one revolution, you know how much flow you can get. Because we can go back in and figure out exactly what that volumetric is. there you go, Viking, again, a gear pump. Every time that thing rotates, you're going to get a certain amount of flow. Is that kind of making sense now, the differences? It's a fixed volume, again, per rotation. Sorry, I got ahead already. Pressure developed dependent upon the system characteristics. It's only going to provide pressure, whatever it takes to get it from point A to point B. It's not going to produce pressure. So you gotta just as we go through this, keep that in mind. What we're going to talk about mainly today is an ANSI process pump, because of all the pumps, we said that there are 78% of all centrifugal pumps, of all the pumps were centrifugal, and within that, about 50% of all those centrifugals are ANSI. Huge amount of process pumps. So what we're going to talk about, does anybody have any idea what ANSI stands for? American National Standard Institute. In other words, when they have this pump, they are dimensionally interchangeable. You can take this pump out and put in somebody else's. It may not be even the same brand, but the shaft height, the volute, your flanges, everything, your feet are all going to be dimensionally interchangeable. Performance varies a little bit, but dimensionally they're all the same. So American National Standard Institute. So we're meeting a standard dimensional data. Does that make sense? Everybody kind of with me so far? And this is basically a cutaway or an internal of the ANSI pump, ANSI centrifugal. This would be your Goulds, your Durco, your Summits, Tony, on your stuff, Summits. For you guys from Mears, this would be your Durcos on the reactors. It's a little bit different, same premise. We'll get into the differences of them. Okay, obviously this is out here on the end. There's a jillion names for this thing. Casing, volute. If you're from Canada, it's a water chamber. Wet end, from that standpoint. This is where your fluid comes in. Obviously this is the suction coming into the eye of the impeller. Here's your impeller right here. And that would be the discharge or the outlet. Everybody with me so far? There's obviously a case gasket to seal between the power frame, or between the stuffing box and the volute. The impeller's right here. That's not a real good picture of the impeller. This is a little bit better diagram of the impeller here from that standpoint. We usually have a cutaway here that's basically, it's a pump cut with 90-degree corner out of it so you can see it. But we don't have that available for this training. You have an O-ring that seals behind the impeller and to the shaft sleeve. This is a stuffing box, seal chamber, and we'll talk more about why we call it that, or back plate. This is your power frame adapter. And we'll go through all these in more detail about what they do. This is the power frame. Again, depends on where you're from. This is power transmission, bearing frame. All you can keep adding to it as you want to. Obviously, from that end back there, that's where all the power is being transmitted through to the impeller. There's your bearing housing. Radial bearing. What's another name for this bearing up here up front? Inboard bearing. Depends on what side of the coin you're on. This would be the inboard because it's closest to the inside of the pump. So it's inboard or radial bearing. And we'll talk about radial a little bit further down the road. Obviously, radial is the forces going this way, up and down, vertically. And we'll talk about those in reference to how it operates internally in the pump. Obviously, that's the shaft from the end right here all the way out to the end. Here's a good example of it out in the middle. And then shaft sleeve. How many of you run shaft sleeves that you know of? Can't you do? Tony, I think you guys do. I know John, Big John over in the rebuild shop uses the shaft sleeves. You guys, and I'll talk about a little bit more of the advantages, disadvantages of using a shaft sleeve. You guys do not, just for your reference, on the stuff that we've installed, do not. The back plate. I don't know why it's doing that again. There we go. There's a good cutaway of the ANSI pump. obviously the impeller, so on and so forth, going back. And when we say 2196, this would be the Gould's version that you're familiar with. And so you know ANSI pumps are, I wouldn't want to call them generic, but there's a lot of people that build them. And so there's different kinds and so on and so forth. This is a off of the original Gould's type. This is what you guys have at your plant. This is the Durco. Same principle. Bearing frame back here, outboard, inboard, stuffing box, impeller. Obviously everything's the same, except yours is a enclosed, semi-enclosed impeller, reverse vane, also same term. Your guys that you're more familiar with on the Gould's is going to be a semi-open impeller. The difference is obviously, this is a Gould's impeller. There's no cover on the front, so it's open. We call it open impeller. Use this out of the way. This has obviously a cover over the front, so we call this a reverse vane or semi-enclosed. Does that make sense so far? And again, I'm going to show you some different variations in centrifugal pumps so that you get a better understanding of what the difference between ANSI and some of these are. This is a what we call an ANSI R. It has, if you notice, see how far this impeller is back from the front of the volute? What do you think that might be used for?
Solids.
Very good, solids. Recessed impeller. It's back out of the pumpage. We're still creating that centrifugal or velocity energy, but back away so that we can get those solids in and out. Through the suction, out the discharge. Stringy material, anything that would be cellulose, something like that would be used in that application. This is not a good picture of this. This is a low flow, high head pump. Again, if you notice, and we'll go through a little deeper, big volute, big giant wheel inside of it, impeller, small suction discharge. In other words, we're going to put a lot of energy into it. In other words, the bigger the wheel, the more velocity, higher the head, higher the pressure, and we'll get to head here in a minute. Here's a better picture. If you can actually, it's not a good picture, but that's what's going to be in that high head, low flow pump. Instead of having a curved impeller or a Francis vane, it's going to be a straight blade. Terribly inefficient. Try to stay away from them if you can because they're just not very efficient. Usually on wash down applications, I don't think you guys have any out there at the plant, but usually wash down, high pressure, again, low flow. This is what we call a general purpose pump. What's the main thing you see there difference than the typical ANSI? Bearing housing, not near as beefy, smaller bearing housing. It also has what we call tangential discharge. See how this pump here is off, the discharge is not off, it's off to the side. So we have tangential discharge. In other words, on the other pumps, go back the other way. Oh, wrong way. We had center line discharge. The volute and the discharge and the suction are in the same vertical line. So you had center line discharge and then you had tangential discharge. Horizontal splits. This is another centrifugal. What would be an advantage of that pump there over the ANSI design? And you'll understand this further as we go down. Basically, we've got a bearing on this side, a bearing on this side, impeller in the middle. We're splitting the load. In other words, we got the impeller out there, we got a bearing on each side of it. Your load across the impeller is the same. So basically, you've got it out in the center instead of having this overhung load on the end. The other thing about them is you can pull that cap. It's not easy, but you can pull that cap and you can basically get to the internals of the pump fairly easy. Just know what it is. Don't go into a lot of, just know they're out there. Another one, this is a multi-stage pump. Basically, the premise is here, suction here, and each one of these stages is going to create a certain amount of pressure. And as we go across there, it's going to get higher. So in other words, if this does 30 pounds, 60, 90, 120, 150, it's a high pressure pump. If you notice, it also has the real close impellers. In other words, it's high pressure. Just keep that in mind, high pressure. Yeah, your Schlumberger Rita pumps. 29 stages. Basically, stacked pump in a can. Tony, for you, it'd be your Grundfos, the boiler feed pumps. You guys don't, you're not in rendering, but over at the you're in rendering, but over at the utilities, Trent's area, they got some of those Grundfos stacked pumps, and that's basically going to be the same premise. Axial flow, just understand that it is high flow, low pressure. See how this impeller in here, it's not even an impeller, it's just a prop. Looks like a boat prop. I mean, literally what it's going to be designed for is huge amounts of volume, 50, 60,000 gallons a minute, maybe 4 feet ahead. It may be going literally over a dike, Lake Pontchartrain down in Louisiana, just for flood control. The other one they used is, what do you call that? Oceans of Fun, whatever, the water parks. What do you call it? The river, lazy river. Basically all they're doing is creating small currents, or huge currents, but large flow, small head. Self-priming pump, this would be your Gorman Rupp. You guys have the MPs, Jaegers, whatever you call them. Don't have any of those? Okay, you guys don't have any self-priming stuff, but know and understand what it is. This is going to be your suction. This is going to be your discharge. As you notice, the flow does not come directly into the impeller. This being the impeller, your flow does not directly come into the impeller. Because of that, that pump always has fluid above the eye of the impeller. When this check valve closes right here, there's a little swing check. That impeller is always going to have fluid above it. So when it goes to start, you may not have any fluid in the suction line, but it can sit there and recirculate that water enough to create a venturi that then it'll start to prime itself. Make sense? Just know and understand what it is. Always the fluid is going to be above the eye of the impeller on a self-priming pump. This is what we talked about earlier. This is API. API stands for American Petroleum Industry. Just know the reason they have this bearing, you see where the feet are to hold that pump, or out here to the side. Typically API stuff is very hot, so you're going to get expansion. You're going to get growth. So we don't want to have it fixed to something that can't grow out or up. Very beefy, huge bearing frame. Vertical turbine. I can't think of anybody in here that has vertical turbine particularly. This is going to be on a cooling tower application. Usually you're going to have a wet well. Water comes back from the cooling tower, and this is going to be at grade right here. And these are your impellers. Just know and understand what it is. It's a turbine, anything in line, high pressure. Submersible, just what it says. This is going to be your flights, Tony, that you deal with. Some KSBs, I think you still have some of those out there. Again, motor, everything in the fluid. What would be a disadvantage of that? Just off the top of your head, anybody?
Shortage, electrical shortage?
Once this seal goes, there's a mechanical seal here. Once that mechanical seal fails, water and electricity don't usually go together very well. So what's going to happen is you're going to flood that motor chamber. It's going to short out, trip out. Nobody's going to be happy. Okay, this is how a pump adds pressure to a liquid. Obviously, we have the impeller here. This is the volute. Everybody getting that so far? This would be the right angle. I have a pointer here somewhere, but I don't know how to use it. Is this it?
I think so. Yeah, you're on right there. You got the pointer up there.
Oh, look here. Okay. Obviously, this is the impeller. You can tell that I'm really technology based here. So, as fluid enters the suction flange at low pressure, in other words, this would be maybe even ambient if we have an open tank When we say ambient pressure, we'll go through that, what that means exactly. So fluid's going to enter the suction of the pump. It's going to be entering at low pressure. Oh, that's a good question there. What is the rotation of the pump? Obviously it says out here it's counterclockwise, right? Does everybody understand how it rotates, that it slings it this way?
Otherwise it'd be pulling it in.
It'd be right. It'd be right. Will a centrifugal pump backwards?
Yeah, probably.
To a degree. Don't run the Gould's version backwards, or even the Durco. It does things, bad things happen, and we'll go into that when we get to the hands-on stuff. Bad things happen. But it will pump backwards. It's usually about 1/3 to 25% of the normal flow and nearly zero pressure. So, what is the, while we're on that topic, just kind of as a little whimsical quiz here, what is the best way to check? What do you do first when you're installing a new pump to verify rotation on an electric motor? Everybody deals in 360 here, or 60 hertz. To check rotation, the first thing we're going to do is make sure it's not coupled together, right? Check rotation on the motor. As you're tearing down and inspecting pumps, be aware that this is going to be a high point of wear. Particularly, Ty, for you where you have a solids laden fluid. For you guys, new well comes in, lots of sand. This is going to be the point where the water, where the oil, fluid, whatever you're pumping is going to wear out right here, one of the places. So just be aware that that's going to be your high pressure point in the pump.
So it'd be washed off in that.
Yeah, and that cut water will be cut back,
It'll like
washed
make
up.
a V in there.
Yeah, it'll cut a V, especially if
It'll
you're,
cut a V into it.
you guys don't have a lot of solids laden stuff at Mears, but if you had anything with solids laden that's abrasive, small particles of sand, anything, ethanol industry would be your mash that you've ground the corn in.
It will reduce performance of the pump.
Yeah, once that wears out, because
Circulate now.
once that opens up,
Going out the discharge is gonna go back, just making a circle.
I just, go ahead and continue around it.
yeah, once that opens up there, your clearances change, and obviously it can go on around, so you're going to flow and pressure is going to be depleted, and then on out the discharge. The stuffing box pressure is in line with the inlet of the pump and the eye of the impeller, which are at low pressure. In other words, we talked about this being the stuffing box. This area here, back plate, whatever you want to call it, is going to be at low pressure. This area right here is what we're referring to as the stuffing box pressure. If you were to put a gauge in that port, this pressure is going to be somewhere between 25 and 30% of your final discharge pressure. The reason it's at lower pressure is as the velocity changes, your pressure gets higher towards the outside. Everybody with me so far? So from that standpoint, your pressure is always going to be lower at the stuffing box. Now, what point in the system would the stuffing box pressure equal the final discharge pressure? What would happen in a system that your stuffing box pressure would see the same?
Shut down.
If somebody shut the valve, yeah, if somebody shut the pump in, now your seal is seeing the entire discharge pressure. Normally it only would see 25 to 30%. So if we were at 100 pounds final discharge pressure, your seal's only trying to hold 25 pounds. Now, if you shut it in, you're shoving 100 pounds of pressure on that seal face. And we'll get into seal face structure here in a little bit. Everybody understand how why that's important on the stuffing box pressure? These are just general guidelines. They are not absolute rules. But in an ANSI pump, Dane, would you agree that that's for the most part a general consensus, that it's pretty much the same? There again, I'm ahead of myself, sorry. And then we go back to this semi-open in-suction back pump out vanes. That would be this impeller right here. On the back, we call these pump out vanes. And what we're doing with the pump out vanes is we're actually pulling the solids back out of that stuffing box area. The reason they're on the back is we want to try to keep those solids moving out into the pumpage. We don't want them to migrate and stay back here. But because the stuffing box pressure is lower than the final discharge, where do you think all them solids want to go? They don't want to go out the hole because that's higher pressure. It's just like a bunch of little kids fighting. They never want to go to least resistance. They want to go to the least pressure, which is in the stuffing box, right? So that's bad. And the reason it's bad, we'll talk about when we get into seals. So just keeping in mind that that's going to happen. If you got solids, you want to keep them moving out into the pumpage. You don't want them to stay stagnant and build up in the stuffing box. The other one is the reverse back impeller right there.
This one?
Yep. The other one is the fully enclosed in suction with balance holes. See those little holes in the back? These are balance holes. The idea there, which one of these two impellers do you, just off the top of your head, which one do you think is more efficient? You think that one's more efficient? This one's actually going to be just, I don't know, 5% typically as a general rule, a little bit more efficient because it has this face on the front and your clearances always stay the same. In other words, this impeller you're going to set off of the volute. This impeller you're going to set off the back plate. So it's a reverse vane. In other words, the clearances are always going to stay the same. It's a little bit more efficient from that standpoint. So obviously on the ANSI, they're saying it's 25% of the total developed head at the suction. So in other words, the stuffing box is going to see 25% as a general rule. On this one, it's only 10% because of how it sets the clearance on the back. On a vertical stage or a Grundfos or something like that, it's going to see the entire full discharge pressure. If you think about it, there was that line shaft pump. As the impellers were all the way down here in the fluid, as it comes up that shaft, it's going to see the full final discharge pressure. So do you understand the difference? Your Schlumbergers are seeing how those are set up are reversed. You're only seeing what your suction pressure is because they're pulling against your motor bearings instead of at your final discharge. Oh, got ahead of myself again, sorry. Who's ready to get rid of some coffee before we go any further?